Hello everybody, today I will be completing the June 2022 Physics Regents Part B2. The last video included Part B1 and the video before that included Part A. So again, I have my calculator here and my reference table. We can begin Part B2. To charge a cell phone battery, 3.69 times 10 to the 3 coulombs of charge is moved through a potential difference of 3.7 volts. Calculate the maximum amount of electrical energy gained by the battery. Okay, so we have to go to the reference table here, and in electricity we want. Okay, so let's name this. So this is gonna be our Q. Is going to be our voltage, and we want the energy, right? So what we can do, voltage equals work divided by charge. Multiply both sides by charge, get work equals voltage times the charge. So to find the work, we have to multiply the voltage by the charge, which is equal to 3.7 volts. Here you wanna write the units down here. 3.7 volts times 3.69 times 10 to the 3 coulombs. Take that as a 3.7 times 3.69. Okay, so let's do this. 3.69 times 10 to the 3, okay, times 3.7. 13653. Or you know what? 1 second. Let me just 3,690. Yeah. Let's just put into scientific notation what we can do. Let's put a decimal point here. Let's round this. So 1.37. Let's just do it like that. 1.3, or you can just plug in this 1.37 times 10 to the 4th. Right, because if we say 1 point here, move it the decimal 4 times. Okay, a 55 kilogram ice skater slides across a level surface and the force of friction. Okay, so this is our mass. This is gonna be our force of friction. Okay, determine the magnitude of the weight. So we have the formula right here. I mean, you shouldn't even, by now you should know, but Fg, force of gravity, this is a formula like you should know absolutely. Force of gravity is equal to the mass times force of gravity, yeah, the weight. So which is equal to 55 kilograms times 9.81 meters per second squared. Okay, let's go right here. 55 times 9.81. Let's just say, round that up, 540 newtons. Okay. Calculate the coefficient of kinetic friction between. Okay, got it. So we have this formula: frictional force equals mu times the normal force, where mu is the coefficient of friction. In this case, it's kinetic since it's moving. He's sliding. So what we can do, solve for mu, you get mu. I'm gonna do my best to try and, okay, that's supposed to be mu equals the force of friction divided by the normal force, which is equal to, we have the force of friction, which is 11 newtons, divided by the normal force, which is 540 newtons. And it has no units because it's a ratio of two of the same units. So 11 divided by 540. And usually you want to see an answer in the zeros. So we can say 0.02. A student produces a wave that is flexible. A student produces a wave in a flexible spring stretched along a tabletop by shaking one end of the spring at a frequency of 2 hertz. Determine the amplitude. Okay, so the amplitude is basically the height from the medium of the wave, from the height to the is basically equal. The distance to the highest part to the lowest part will be the same, but it's from the median line. So the median line cuts through the middle of the wave. So if you were to imagine this right here, that's the median line. So the amplitude will be the distance from here to the top, or the distance from here to the bottom. It has to be equal. So since we have 1 meter here, we can just divide by 2, right? 1 meter divided by 2, this is 0.5 up, 0.5 down. So it's going to be, determine the amplitude is going to be 0.5 meters. Determine the wavelength. Okay. So what do we, the wavelength, right? The wavelength we know is 1 crest, 1 trough. So we go up right here. We go up 1 crest, 1 trough. That's a wave. The wave ends right here. Starts right here, ends right here. Let's put that right here. Okay. Again, you see 1 up, 1 down. 1 up, 1 down. That's 2 waves right here. 1 up, 1 down. Take it like that. Assume that's right there. That's 3 waves. So we have 3 waves right here. Now, to find the wavelength of the wave, we have to find basically the length of 1 wave, not 3 waves. So we have to find whatever the length of the 3 waves is divided by 3 to find the wavelength of 1 wave. Because that's what the wavelength is. So we have 4.5 meters measures the whole thing. So we can do 4.5 meters divided by 3 waves is equal to 1.5 meters. Okay, next. 100 Newton box is pulled up a 20 meter long incline by a constant force of 80 newtons. The vertical height gained by the box is 10 meters. Okay. Determine the total work done in joules. Okay. So what is the work formula? The work formula is equal to the force times the displacement. So what is our force here? You cannot assume that this is our force because this is just the weight of the object. The force is the basically the external force applied to the object, which is in this case is 80 newtons traveled over a distance of 20 meters. So work is equal to FD, which is equal to the force, 80 newtons, and this is the total work done by the system, 80 newtons times 20 meters. Now, the only case you would use this 100 newtons is when to find the gravitational potential energy, if they ask us. So 80 times 20. Oh, that's just, that's 1600. Yeah, you could 8 times 2 and then add the 2 zeros, I forgot. It's 1600 joules. So this is the total work done, not including the gravitational potential energy, the loss due to friction if there is, or the kinetic energy. Determine the total amount. Okay, so now they ask for the potential energy. So potential energy is equal to, where's the formula here? Right here, mg delta h, right? So the change in energy, potential energy, is equal to mg delta h. which is equal to the weight. So mg is the weight. What's the weight of the object? 100 newtons. Times the change in height. What's the change in height? Well, we assume this is 0, so 0 to 10 is 10. Right? So then we get, let me fix that, is equal to 1,000 joules. So this is the potential energy, right? So due to mechanical energy, right, here at the lowest point, the kinetic plus the potential has to equal the same at the highest point. So assume here the potential is 0, P, E is 0 because the height is, let me write this better, sorry. The potential equals 0 because it has no height up from the ground. And then the kinetic energy is 1/2 mv squared. Well, we don't know, whatever, blah, blah, blah. Let's assume. Let me see, because we don't have the velocity. But let's assume it's 20 joules, okay? Whatever it is. Doesn't matter. That's not the point. Here, by conservation of energy, we need to say that, because energy can neither be created nor destroyed. So here, the potential energy, we assume it's at rest here at the top. So potential energy, oh, that shouldn't be, potential energy equals 20 joules now. Oh, no, got it. So in this case, it's 1,000, assuming, so the kinetic would be 1,000 here, assuming the energy is conserved. Joules, and then the kinetic will equal to 0 joules because it's at rest. So then, okay, just understand that. We explain why there's a difference between the total work done by the 80 Newton force in pulling its box to the top of the incline and the amount of gravitational potential energy. So it's basically saying why is a difference in this value and this value. Well, look, the total work done represents the total work done without any loss of friction, right? The potential energy is just 1,000 joules, but in this case, there's a difference between the total work because some of that work, 600 joules in this case, right, was lost. So we say lost to friction. It was converted, right, to heat when it was going up across the incline. So let's just write friction. You see, because in total there was supposed to be 1,600 joules, because like I said in the beginning, this work represents the total work done without any account to loss. But we had 1,000 joules, which meant we lost some of that energy, the 1,600 joules. And we lost 1,600 minus 1,000, so 600 joules, we lost it due to friction when we were bringing it up the incline. The diagram below represents an electric circuit consisting of a 110 ohm resistor and 220 ohm resistor connected to a source of potential difference, which in this case is 6 volts. So calculate the equivalent resistance of a circuit. So we have a parallel circuit here. We need the equivalent resistance of a parallel circuit. So it's equal to 1 over Req. So 1 over Req is equal to 1, we can just plug in 1 over 110 ohms. So in this case, okay, let's just write the whole formula down. Plus 1 over R2. So we have 2 resistors in this case. And then we set it equal to 1 over 110 ohms plus 1 over 220 ohms. Multiply this by 2 to get common denominators. We get 2 over 220 plus 1 over 220 is 302 over 20 ohms. And then we have this is equal to 1 over REQ. To find REQ, we take the inverse, right? We basically flip it. So we have to flip this too. So 220 divided by 3 is, let's see, divided by 3. That's 73.3. That's a weird answer, but it's going to be 73.3 ohms. Calculate the total current in the circuit. So if we have the resistance, we can find sorry. We can find the total current now. The way we can do that is we can use this formula, R equals V over I, which means that multiply both sides by R and I divide by R, we get I equals V over R, which is equal to the voltage of the circuit, which is equal to 6 volts, divided by the total resistance, which we have is 73.3 ohms, equal to 6 divided by answer, we get 0.08 amps. 0.08 amperes. Okay, so we've done, yeah. Okay, compare the power dissipated by the 110 ohm resistor to the power dissipated by the 220. Okay, so the power dissipated by the 100 ohm resistor, so we have the formula right here. Power, this one, power equals, we want to see something with resistance so we can compare. Okay, power equals, I think I got it. Power equals V squared divided by R. So compare the power dissipated by the, so since the power is inversely related to resistance, so the more resistance we have, the less power we have. So if we had a 110 ohm resistor compared to a 220 ohm resistor, the power dissipated by the 110 will be double because it's inversely related. So the power by, let's just say power of 110 ohm is greater than the power of the 220 ohm. It is double. Okay. In this case, you couldn't use I squared R because then we would have to find the current in each individual circuit, because in a parallel circuit, the current is equal to the current of each individual one added up. Okay, that's the best way to do that one. Okay, yeah, that's the end of this video. The next video will include part C, which will include all the rest of these questions. Yeah. Okay. Thank you for watching, and again, as I said, the next video will include part C.